Hi guys, welcome to today's video. Today we want to talk about the kinetics of enzymes in the case of competitive inhibition. Now what is competitive inhibition? Now let's say this is the normal kind of enzyme kinetics. So E plus S becomes ES, E being the enzyme, S being the substrate, ES being the enzyme substrate complex. And of course, this ES becomes E plus P, which is the enzyme and the product. So the enzyme is a catalyst basically. And we assume over here that there's only the forward reaction. This is the classical Michaelis-Menten, I'm not sure how to pronounce, the MM equation. I just called that here, alright? So this is the vanilla Michaelis-Menten equation, or the initial rate kind of equation where the backward reaction is basically negligible. Now this being the vanilla one. This is the vanilla one. Vanilla mean, of course, is the plain one without any kind of special kinetics. Now what happens if we have an inhibitor? An inhibitor, we just call it I. And the inhibitor, what it does, the inhibitor binds competitively to the enzyme. So let's say you have your enzyme here, E, and this is your active site. So the inhibitor will bind to the active site of the enzyme so that the substrate cannot bind to the enzyme. Now likewise, of course, if the substrate is bound to the enzyme, then the inhibitor cannot bind. So this is known as the competitive inhibition scenario. Okay, so the inhibition scenario, well, you'll have this case. Let's say there's a reversible reaction here, and then you'll have K3 forward, K minus 3 backward, and you have EI. So what this competitive inhibition does is that it renders a good fraction of this enzyme, of the total concentration of enzymes, basically inactive. Now let's start deriving it. Let's go back to the basics. We have the V equals to the dP dt again, and that will be K2 into ES. So that's step 1. And now you want the mass balance of ES, the species ES. Okay, the ES dt, and the ES dt, and that will be equals to the forward reaction and the rate of the forward reaction minus the rate of the backward reaction. So let's have K1 into E and S forward minus K minus 1 ES backwards. That's 2. So K1 forward, K minus 1 backward. And now let's have another balance for the enzyme species. Okay, so E0, which is the total enzyme concentration, equals the concentration of the free enzymes E plus enzyme substrate complex ES plus enzyme inhibitor complex EI. Now you can probably see now how this is going to get a little more complicated now that you have this extra variable EI. And what do we do about that? Well, we'll need to do another equation here. I believe we have this, dEI dt equals to the forward rate, K3 E into I, minus the backward rate, K minus 3 into EI. Okay, so now would like to have some simplifying assumptions. So today we want the rapid equilibrium just take that for example. That's a very simple one, where the forward and backward rates of these are pretty much equal. So rapid equilibrium is established between E plus S individually and the enzyme substrate complex ES and E plus I. This is the second equilibrium that is also quickly established. That is our assumption. E plus I individually, enzyme and inhibitor individually, is in equilibrium with the enzyme inhibitor complex EI. So that's K3 forward, K minus 3 backwards. So let's put the minus a little clearer. Okay, K minus 3. So that's the backward reaction. Now, under these rapid equilibrium assumptions, we'll have to assume, we'll have to assume the forward and backward rates are equal. Okay, I think I forgot one more. I forgot one more here. So the ES dt, it is the forward rate over here, the forward rate of production of ES minus the backward rate. And then of course there's this rate which I forgot to put in. Now this is K2 into ES. Okay, no problem. Okay, so the forward rate and the backward rate are equal. So all this becomes 0. Okay? So here is the other one. dEI dt. All this is just basically 0 in the rapid equilibrium assumption. Okay? So essentially, dES dt is just the rate of consumption of ES during the during the production of the product. Okay? And not only that, we have to basically write this down so that we know the kind of equilibrium conditions. Oopsie. Okay, never mind. Let's write that again. K sorry. Sorry for the delay. Anyway, just distracted a bit. Anyway, so K1 E into S forward, K1 E into S forwards equals K minus 1 ES. Okay, so let's just shift this around. Let's just shift this around so that we have ES on top, E and S on the bottom. So we'll make ES the subject equals to K minus 1 over K1 into E into S. Likewise, K3 E into I equals to K minus 3 into EI. This is under rapid equilibrium, so I'll do a similar thing. Okay, so this goes to the bottom. K3 over K minus 3 into E and I. Okay, so now I can substitute this back into this equation here. All of this I can substitute back into this enzyme balance equation, or rather, this I can substitute here. I need to substitute something for the E. Okay, so I want, at the end of the day, let's put it simply, at the end of the day, we want this ES term to be in terms of something we can measure experimentally. So we need to make ES the subject here. We need to substitute an expression for E and substitute an expression for EI. So let's continue. ES equals E0 minus EI minus concentration of E. So EI will be this lot here. So I have E0 minus K3 over K minus 3. Let's have E into I. Okay. And we'll need the expression for E here. So instead of using the same equation again, because that will kind of be redundant, we need to substitute something else. Because if we substitute these two things in, they might as well just cancel out, you see. So you'll need something a little different. So instead, you have to put this in so that there are enough equations to define everything. So let's see. Let's have E into, so we'll bring this over K1 over K minus 1. So we'll bring this over. We're swapping it over. We're dividing both sides by this factor. Okay? And we divide it by S. So ES is on top. This one is flopped around. And this one is at the bottom. Okay? So that's E. Minus K1 over K minus 1. ES by S. And as usual, we can just bring it over to this side and divide everything at the bottom. And one more thing, there's an E here as well, which we will need to deal with. Okay? So for a start, we might want to factor E out first before we do anything messy. This E0. We want to eliminate all E's. Okay, we'll factor out E first. So I have a plus E, and you have a K3 over K minus 3 into I, and I'll have a minus 1 here. Okay, I'll just substitute this E out, and I'll factorize this E out because this whole thing here is E. So I'll just bring that out first. And then I want to substitute this in so that I can get ES out. And now E0 plus K1 over K minus 1. Let's have ES over S. And then we have K3 over K minus 3 into I, and that minus 1. So this we can bring to the left-hand side. So let's do just that. And by doing that, we will collect all our ES terms together. So let's write the original first. That's K1 over K minus 1, ES over S, minus K3 over K minus 3 into the inhibitor concentration minus 1. Bring this over. So ES will be on the left hand side, and I will have plus, let me write that later. So I'll have plus, I will convert these to a positive sign because I'm bringing it over. So K1 over K minus 1. And you have ES over S. Now multiply by K3 over K minus 3 I into plus 1. I mean I and then the plus 1 there. Okay. So hope there's no issue so far. So it's a plus 1. Okay. Everything clear? I hope so. Yeah. And you have this E0 on the right hand side. So So now I can just factorize. I can factorize this ES out. And I'll have this really big bracket. And I have 1 plus K1 over K minus 1, 1 over S, K3 over K minus 3 into I have that bracket plus 1, close bracket, and close. And that will be the equation. And now I'll just bring this lot to the bottom. ES equals to E naught over 1 plus K1 over K minus 1, 1 by S into K3, K minus 3 to I plus 1, close. Okay, so that is our ES. Let me close this for proper, to write it right properly. And let's get it written well. Let's tidy up the denominator in a bit. Anyway, let's tidy up the denominator. So this is over 1 plus. Yeah, so the first thing to tidy is this, all these k values. Let's just call this km prime. We define km prime as k1, k minus 1 over k1. And we will define another one for the inhibitor, ki equals to k minus 3 over k3. Okay, so this is just here though, these are the equilibrium constants meant to help us tidy up. So 1 over, so this is the km prime at the bottom, km prime, 1 by concentration of S. So 1 by the concentration of S. Okay, and then I will have 1 by Ki, so that is I over the Ki here, and now have 1. So concentration of I over Ki and plus 1. So multiplying that out, we will get this. E naught over 1 over 1 km prime, 1 over S. So I will have the I on top and Ki at the bottom. Then I will have plus 1 over km prime, 1 over S. There you go. Now I have the ES value. I can just substitute that back into the first equation. Then you will have V equals to dP dt, and that will be equal to K2 into ES, which I will just substitute directly here as 1 over this. Whatever this is, the whole chunk at the bottom. I'll just put the bracket I on top, and I'll make this over the Ki. So I over Km, concentration of S and Ki, plus 1 over Km prime into S. And of course, we will want to multiply S throughout so that we will, make it neater. So multiply S to the denominator and numerator. I mean just the numerator of the denominator and numerator of the numerator. You see. So multiply S to top and bottom. Okay, so K2 E naught into S over S plus, so I'll multiply this to the top. So we have S concentration of S concentration of I over Km prime Ki plus S over Km prime. Okay? And this we've kind of recognized probably from the last videos as the Vmax equals the K2 E naught. Okay? And that will be Vmax S over S plus S over Km prime 1 plus I over Ki. And, well, okay, I think I forgot something. So this should not have an S. This is just 1. Because the S is on the bottom. So I just have to cancel this out and put a 1 here. Okay, so that's basically it. The modified Michaelis-Menten equation. And let me write that again just for neatness sake. Vmax equals to, oh wait, no. V equals to Vmax into S over S plus 1 over Km prime 1 over Km prime into I 1 plus concentration of inhibitor over Ki, the equilibrium constant. Okay. Oh, I think I found my careless mistake. There you are. Anyway, yes, this should have been this is K1 over K minus 1. So K1 is here, K minus 1 is here. So ES is K1 over K minus 1. Okay, so that means wherever I have this Km prime, okay, so tracing back I have to, this is, you know, opposite. I need to flip this, which means I need to flip this and trace it down. It just means this should be Km prime here. Anyway, yeah, that's just one careless mistake. Right here, I did it here. So just watch out, yeah? But other than that, yeah, I'll just put this careless. Yeah, make sure not to do that in your exams, but yeah, it's kind of a time waster. But anyway, this is the final product you should get. And what does that mean actually? Well, we can see that Vmax is constant, and you know the expression S is constant as compared to the vanilla Michaelis-Menten kinetics. So we have S plus Km prime. Yeah. So compared to the normal Michaelis-Menten, we have to recognize that all these two terms are the same. This term is multiplied by this term here, which is the inhibition, I think, and this is greater than 1. So it means that the denominator is bigger, and if the denominator is bigger, that means that the overall rate at any concentration of S will be slower. So that's how the kinetics of the inhibition, competitive inhibition are. And we have effectively, aside from the careless mistake, derived our Michaelis-Menten equation for competitive inhibition. So thanks for watching. I'll see you guys next time. Bye-bye.